Hey everybody, today I'm going to talk about the mole, and we've talked already in class about that the mole itself is just a fancy name for a very large collection of small things like atoms or ions, molecules, that sort of thing. And we know that Avogadro's number, that is the number that is attached with this name, the mole, is this really large number here, 6.02 times 10 to the 23rd. What I want to talk to today is the connection between this number and the numbers on the periodic table here. Okay, so we're going to talk about how Avogadro's number came to be. Why is this a special number? And why do we care that we have, why is this number of atoms important? Okay, that's what we're going to talk about. So what I want you to do is I want you to look at this periodic table, and I want you to notice, first of all, the numbers. You see all the numbers there? Now these numbers, you may or may not know how these numbers are calculated or what these mean. But these numbers, each proton in, let's say, vanadium, for example, so let's focus in on vanadium here. Each proton in the vanadium atom is one atomic mass unit, okay? One AMU. Now, the AMU is basically, it's just an arbitrary unit for the mass of one proton. And a neutron is almost identical, so that's the mass of a neutron as well. So one AMU is the mass of one proton and one neutron as well. Okay. Now, why is this? Why are these numbers important? Well, the way these numbers came from, okay, where these numbers came from are the average mass of all of the typical vanadium atoms. That would be 23 protons and about 27 neutrons. Okay, that's the mass of all the typical atoms of vanadium in atomic mass units, plus the weighted average of all of the variations of this. So all vanadium atoms have 23 protons, but some have different numbers of neutrons. Okay. And so when you take into account the relative abundance of the, and I call them kind of the cousins, the cousin versions, okay, of vanadium, the average mass for one atom of vanadium, or a typical atom in vanadium, of vanadium, is about 50.942 atomic mass units. All right, so that's the average mass in atomic mass units. Now we do notice that all of the elements have a number attached to them, right? And so when we talk about atomic mass units, those units aren't very helpful in the lab. If we're going to mix together, some hydrogen and some beryllium, how do I take one atomic mass unit and roughly 9 atomic mass units? Like what is that? Well, that's one, atom of hydrogen and one atom of beryllium. Well, I can't do that. I need to take some other mass, and typical in the lab is grams. We like to deal with grams, right? And so the question then becomes, how many atoms, can I take of hydrogen that would be a workable amount of mass in grams? And I want you to think about this. Let's take hydrogen and beryllium. Let's take a look at those. Beryllium is almost exactly 9 times as large as hydrogen. See that? Because we have a number, we have 9, and we have a number of 8 for as far as average mass, okay? So that's about 9 times as much. If I had one atom of hydrogen or one atom of beryllium, the mass difference would be about 9 times as big, right? The beryllium would be about 9 times as large. If I had 1,000, okay, let's think about this for a second. If I had 1,000 atoms of each, okay, whatever sample that would still be about 9 times as large, the beryllium. You see that? What if I had, lots? What if I had more and more, but the same amount of each? So let's say I had 1 billion, okay? So, okay? So I've got a billion, right? 1,000, million, billion. 1 billion of each. 3, 6, okay, 9. All right. The relative mass would still be about 9 to 1. You see that? Now, how many grams would I have if I had a billion atoms? That's still not a lot. You know, that's still a very small amount. But if you had a billion atoms, like we're talking, you know, zeros out to nowhere. If you had a billion atoms, then you might have something like, you know, half a gram or something. Oh, I'm just roughly about half a gram. Okay, and then you'd have roughly 9 times as much, you know, grams of this one, right? Brilliant, right? About 9 times as much. So the scientists kind of got to thinking, well, look at this. How many would I need? How many atoms would I need for us to have 1.008 grams? It would be the exact same number of atoms that I would need of beryllium to have 9.012 grams. Do you see how we're inching up to that? You see? So how many, what's the number of each, each atom? What's the number that would get to this many grams? And that's where Avogadro's number comes in. After, after experimentation and observation and stuff like that, they've come up with this number of Avogadro's number, and the significance of it is this. It is like the conversion unit. Okay, let me get rid of some of this stuff. It is like the conversion between atomic mass units and grams. So look at this statement. The numbers for each element, okay, and I'm talking about these numbers here, these mass units, is the mass in grams of 1 mole of that element. So, what I'm saying is that if you had exactly 6.02 times 10 to the 23 hydrogen atoms, that would be 1.008 grams. And if you had 6.02 times 10 to the 23rd beryllium atoms, you would have 9.012 grams. That's why this number is special. This is the number that connects atomic mass units with grams, right here. Okay? And it's called Avogadro's number, named after Avogadro, who did a lot of work in this area. He didn't come up with the number himself, as far as I understand, but it's just named after him. But that's the significance, okay? It's this many atoms connects the atomic mass unit number with the number of grams. So if we look over here, okay, anywhere else in the periodic table, right? Aluminum. 6.02 times 10 to the 23rd aluminum atoms weighs exactly 26.982 grams. Isn't that great? That's awesome. That's 1 mole of aluminum atoms, and we know exactly how much it weighs. And so that's where that number comes from. There's your quick lesson on where Avogadro's number came from. Sorry, my notes are like a little crazy on me. I'm not sure why we're doing that. But anyways, Avogadro's number, that's it, and that's where it comes from.